Okay, let's have a look at the answer to this question then. We're told that we shine ultraviolet radiation on a clean metal surface in a vacuum and that we get electrons emitted. So instantly we know that the energy of our photon is greater than the work function, or at least equal to, because we are getting photoelectrons emitted. We are given the photoelectric equation and it wants you to state what everything is. So first of all, HF. Well, if you didn't remember outright, try and remember that E equals HF, where E is our photon energy. So HF is just the photon energy. Now this symbol here is our work function, and getting the marks for this involves a little bit more than saying just the work function. If in doubt, put more information than you think you need and say that the work function is the minimum energy that a photon needs to release a photoelectron. And I'm going to abbreviate photoelectron to PE for the sake of these answers. Final part is asking us what EK is. Now instantly we can see that that is a kinetic energy, but just saying kinetic energy wouldn't be enough. In fact, if you look at the energies that we get from a released photoelectron, which is of course what's left over from the energy of my photon, because the energy of my photon is equal to the work function plus kinetic energy, then I need to be specific and say that it is the maximum kinetic energy that a photoelectron will have. Now let's look at the next part of the question. And the next part is saying now we have taken away our UV source and replaced it with a source of red light. And of course the frequency of red light is much less than the frequency of our UV. So we know this is going to have an effect. We're now told also that the intensity is the same, but don't forget intensity has no effect on whether photoelectrons will be released. It only affects the number that are released if the incident photon has enough energy to trigger the release of them. So we're told that the frequency is less than the work function over Planck's constant. And that's significant because from E equals HF, where F is our threshold frequency, so if we're trying to state the situation where this is just going to happen, and if we say that E in that situation is the work function, we have work function equals HF, and so we can rearrange that to get that F is equal to the work function divided by H. So if the frequency of my incident photon is less than the work function divided by H, then I know that my photon isn't going to have enough energy to release a photoelectron. So the result of this is that no photoelectrons, and remember I'm abbreviating it there, are released. However, the wave theory of light would predict something different. The wave theory would predict that photoelectrons are released. But it would just take more time. Because remember, if light really did travel as a wave, eventually my electron would be able to absorb enough energy to escape. Final part of the question says use the photon theory of light to explain the effect of using the red light source. So this is wanting us to do two things. First of all, to explain the principles of the photon theory of light, and then explain why the red light source had no effect. Well, there are a couple of things we always need to remember for this. The first being that an electron can only absorb one electron. And if that electron photon has energy that is less than the work function of the material, no photoelectrons are released. So that's explaining the photon theory. Now what's the effect of the red light source? Well, this is where we just say that red light has a frequency less than the frequency of UV, and since E equals HF, it has less energy. Now, as it happens here, the energy of the red light is less than the work function, therefore no photoelectrons can be released.